join us during the webinar. And we will be recording this meeting and we will upload it later on YouTube. So those who came late can rewatch the webinar on YouTube. So again, good morning, good evening, everyone. I'm Sohaila, and I am really happy to welcome you to our today's webinar, Simulating the Atom, Nuclear Codes, Modeling, and Digital Twins. Before we begin, I want to remind us why we are here today. We are here today because this was a collaboration between RNEA and the Student Union of Alexandria University, and we are doing this students to students, connected by atoms, driven by youth. And I think today's session reflects this perfectly. Today we won't talk, we will not talk only about theory. We will talk about how we actually understand, predict, and interact with systems we can't even see, and sometimes can't even physically access. So we will go from AI models to digital twins, all the way to real-world nuclear applications. So by the end, you will see how everything connects together. So, and honestly, we have a really strong lineup of speakers today. So I'm excited for you to hear from them. So, like a couple of quick notes before we start, I would love this to be interactive. So please drop all of your questions inside the chat box. We will answer them in the end. Like, don't overthink them. The more you are curious, the better. So we will discuss them together at the end. So let's get into it. Let's start now with Ali. Our first speaker for today's webinar is Ali. He will take us into the world of digital twins, and I'm really curious about this topic. Please, Ali, you can start.
Hello everyone, my name is Ali. I'm from Egypt. I'm a second-year master student in mechatronics and robotics at Moscow Power Engineering Institute. And of course, I'm a Russian nuclear education ambassador. Today, I will speak with you about how robotics and mechatronics bring nuclear simulations to life. So, when we start to talk about simulating the atom or digital twins for nuclear plants, we usually think about physics, math, and powerful computers. And that makes sense. This is the core of it. But I am here to talk about something a little different. I am a mechatronics and robotics engineer, and my job is to build the tools that make those simulations useful in the real world. So think of it this way. Scientists give us the map of the nuclear world. We build the vehicle that can actually drive around the map. So in the next few minutes, I will show you how robots and smart systems are helping make nuclear energy safer and more efficient. So if we go to the next slide, we will see the contents today. We'll speak about 7 things. And also if we go to the next slide, we will start with the problem. So why we can't send humans? First, let's understand the problem. Why we do even need robots in nuclear facilities? Answer is because it's one of the most dangerous places on the earth for a human. 3 big reasons. First one, the radiation. It can make you very sick very quickly. You can't even stand near a reactor core for more few seconds. Second thing, it's the heat. It's incredibly hot. No human can get close to the parts of the reactor. And third one, it's no access. Many parts of a nuclear plant are sealed shut. They are too dangerous to open for years. So the question, how do we check if everything is working? How do we fix something broken? How do we handle the waste? So we can't send humans to fix these problems, so we send robots. So if we'll go to the next slide, now you might have heard the term digital twin. So what does it mean? Imagine you have a video game. We all playing video games. I think we have the video game of the nuclear reactor. a perfect copy, but inside the computer. Every pipe, every valve, every screw has a digital version. Now this digital copy is connected to the real reactor. Sensors in the real world send the data to the computer all the time. So the digital twin knows the real temperature, the real pressure, the real radiation levels at this exact moment. So why is this useful? Because we can use digital twin to predict the future. We can ask about what will happen if we turn this valve. When will this pipe break without even touching the real reactor? You know, it's like a flight simulator for a pilot. You can practice and make mistakes safely without crashing the real plane. So if we go to next slide, we speak about the role of mechatronics. So where do I and another mechatronics engineers fit into this picture? The digital twin is great, but it's just a prediction. How do we know if it's correct? We need to check it against reality. Of course, everything we need to check it against reality. We need to send something to touch, measure, and look at the real reactor. That something is a robot, and mechatronics is what makes this robot smart. So mechatronics is just a fancy word for combining three things. First thing, it's the mechanical parts. It's the arms and the legs of the robot. Second thing, electronics and sensors. They are the nerves and the senses. Third thing is the computers and control systems. It's the brain of the whole robot. So we build robots that can go into dangerous places, sense what's happening, and send that information back to the digital twin. So we close the loop between the virtual world and the real one. So next slide, we will see one example. So this example, I want you to imagine a pipe in the cooling system. The digital twin has been running simulations. It predicts that this pipe will fail in 6 months. It's getting weak somehow. So in the old days, you would have to shut down the whole plant and send humans to check that plant and what happened there. This costs a lot of money and puts people at risk. But with our approach, we send robot. This robot uses a digital twin as a map. It knows exactly where to go. It climbs through the plant and find the pipe, use the sensors to measure how thick the pipe wall really is. So the robot sends this real data back to the digital twin. If the pipe is fine, the digital twin updates its model and learns that it was wrong. If the pipe really was weak, we know exactly when to shut down for repair. No one will guess anything, no unnecessary risk, just smart maintenance. So in the next slide, you will see the second example. It's another big job is handling the nuclear waste. This waste is dangerous for thousands of years. We store it in special rooms called hot cells. These rooms are behind thick wall of concrete and lead. Inside, there are robotics arm. Outside, a human operator controls them. This is a pure mechatronics action. The operator moves by joystick. Electronics send the signal back to the robot, and the robot mechanical arms copy the movement exactly. But we add one more clever thing. It's called touch feedback. If the robot touches something, the operator can actually feel it through the joystick. This way, they know if they are grabbing too hard or too soft. So it's like being inside the room, but without the danger. And before any real movement, they can practice on the digital twin. They can make sure the path is safe. Then they tell the real robot to do it. It's absolutely zero risk. So if we look at the next slide, we will uh, speak about what I am personally working on. So in my master's research, I focused on three things. First thing, it's control. I'm trying to make robot arms smarter. When they pick up something heavy, they should adjust automatically, just like human would do. So I write codes that helps them feel the object and adapt. Second thing, of course, AI, because now we're using AI. I'm using AI to look at the data coming from the robots. The AI can find and help the digital twin make better predictions automatically. And third thing, it's a design. So now I'm working and building a small robot prototype that can go under the water to inspect the nuclear fuel rods. It's somehow fun challenge because water and electronics don't usually mix well. But my goal is to make the systems a little more intelligent and a little more useful for the nuclear industry. So if we go to the next slide, we will see the challenge that we still face. Of course, we are not done yet. We still have big challenge. So first one, it's radiation. It destroys normal electronics. So we need special uh, parts. We need to make robots that are cheap and easy to replace. Second thing is communication. So when you control a robot from far away, there is always a small delay. If the signal cuts out for 1 second, what should the robot do? Should it stop? Should it keep going? So we need to build it like somehow smart and positive safety features. The third thing is autonomy. How much the robot decides on its own. Should it wait for the human to send them like what to do, or can it handle small problems by itself? These are like the main problems that we are trying to solve and I'm working on. So if we'll go to the final slide, is the conclusion. So let me leave you with one simple idea. Simulation and digital twins give us knowledge. They tell us what might happen, but robots and mechatronics give us the power to act on the knowledge safely. We need like to build tools to let the humans reach into the places we couldn't never go before. We connected the safe, clean world of computer models to the dangerous real world of nuclear energy. It's an exciting field to be in, and I'm happy to be part of it. Thank you for your listening, and I'll be happy to answer your questions.
Thank you so much, Ali. This was a great way of telling us how simulations are not just abstract models, but something we can actually act on in real systems. I especially like the idea of using like this as a navigation system for robots. It was really clear and to understand this topic in an easy way. So now we are moving to our next speaker, Basil. Basil is going to take us into one of the most challenging areas in nuclear engineering, which is the commissioning and how digital tools help manage something that can last decades. Basil, the stage is yours.
Thank you very much, Sohaila. So good day, everyone. Thank you for taking the time to join us today. My name is Basil Shaheen, and I'm a PhD researcher at Bauman Moscow State Technical University. And I'm focusing on product quality management, standardization, and production organization. I also have a background in mechatronics and robotics. So today, I'd like to walk you through a topic that sits right at the crossroads of cutting-edge digital technology and one of the most demanding engineering challenges we face, which is digital twins for nuclear decommissioning, or more specifically, looking at robotics, safety, and logistics. So to begin, here is how my time with you is structured for today. We'll begin by clarifying what nuclear decommissioning actually means. Then we'll cover the basics of digital twin technology and, importantly, why it matters specifically for decommissioning work. From there, we'll dive into the three core application areas and which are how robotics enable work in places humans can't go, how predictive safety modeling protects workers, and how logistics coordination keeps massively complex projects on track. We'll wrap up with a real-world case study from the EU and a quick look at where this field is heading. And finally, my key takeaways. Now, let's begin. So what exactly is nuclear decommissioning? So the IAEA defines it as the administrative and technical process of permanently shutting down a nuclear facility and reducing residual radioactivity to safe levels. So it's a simple definition, but complicated reality. So we're typically talking about a process that takes anywhere from 20 to 60 years for full site clearance. And 4 challenges make this especially difficult. First one being strict regulations. So every single step has to comply with rigorous safety standards and environmental tracking, where there is no room for shortcuts. Then there is cost. So we're not discussing thousands or millions here, but individual site remediation often runs into the billions. Then there is radiation. So in many work zones, dose rates are simply too high for humans to enter safely, sometimes exceeding 100 millisieverts per hour. And fourth is legacy infrastructure. So many of these facilities were built decades ago with outdated documentation and complex layouts that weren't designed with decommissioning in mind. So if we go to the next slide, so let me put some numbers to that. So according to the IAEA's PRIS database, as of 2025, roughly 190 reactors worldwide have been permanently shut down. Of those, more than 50 are currently in the active decommissioning phase. So in the UK alone, the Nuclear Decommissioning Authority oversees 17 complex legacy sites. And across the EU, over 10 member states are now coordinating efforts through digital initiatives like the Dorado project, which we'll touch on later. But perhaps the most striking number comes from Sellafield in the UK. An estimated cleanup cost of 130 billion British pounds spread across a 120-year timeline. That's not just a project, that's a multi-generational commitment. And it's clear that traditional project management approaches aren't enough, and we need better tools. So why digital twins? So traditional decommissioning planning has real limitations. So physical access to high radiation zones is restricted, manual planning introduces uncertainty, and when problems arise on site, teams often have to react in real time, which is risky and expensive. So a digital twin changes that dynamic. At its core, a digital twin is a dynamic virtual replica of a physical asset, continuously updated with real-time data from sensors, IoT devices, and operational feeds. So what does that buy us? Well, a few big things. So we can pre-visualize complex dismantling sequences before any physical work begins. We can simulate worker movement to optimize radiation dose, staying aligned with the ALARA principle. We gain better predictability on cost and schedule, and we can auto-generate the documentation regulators required. So as the IAEA noted in a 2022 technical meeting, digital twins enable what-if scenarios without physical risk. That ability to test, iterate, and optimize in a safe virtual space is transformative. So just to ground this technically, the architecture typically has 4 layers. The physical asset itself, the data connection layer, so sensors, IoT, the virtual model, often built in 3D or BIM, and finally, the analytics and AI layer that turns data into decisions. The key is that these layers stay synchronized in real time. So now let's get into applications, starting with robotics. The constraint is straightforward. If dose rates exceed safe limits, humans can't go in. So we send robots instead, but with a critical upgrade. They're guided by the digital twin. So take inspection and radiation mapping robots, for example. Quadrupedal platforms can navigate uneven, debris-filled terrain that wheels or tracks might struggle with. They carry sensor suits, so LiDAR for 3D mapping, gamma detectors for radiation levels, and cameras for visual context. But here's where the digital twin adds value. So operators can pre-program robot paths in the virtual environment first. They can run collision checks, verify reachability, and rehearse the mission, all before the robot ever enters the zone. And during the actual operation, real-time sensor data feeds back into the model, giving the operator enhanced situational awareness. So it's not just a remote control, it's informed, predictive teleoperation. So next up, we will look at heavy-duty dismantling. So for lighter tasks, that works well, what we talked about previously. But what about heavy-duty demolition? Cutting concrete, removing reactor shielding. So here, engineering trade-offs matter. You'll often see hydraulic systems preferred over electric actuators for this kind of work. So why is that? Well, electric robots, like standard industrial arms, are precise, but they can be fragile under sudden shock loads. So as we know, demolition isn't smooth or controlled or anything like that. It's just high frequency, impact, and vibration. A hydraulic system like those on a Brock robot is built to absorb that kind of stress. So the key advantage is of force density. So hydraulics deliver much higher braking force per unit volume, which means you can fit a powerful, compact robot in tight, complex spaces typical for reactor buildings. And stability is also engineered in. So these robots have a lower center of gravity, wide track base, force application close to the ground, and crucially, all of this is validated first in the digital twin before any physical deployment. So let's shift to our second pillar, safety. So digital twins move us from reactive safety, which is responding to incidents, to predictive risk management. So in the virtual environment, we can model how contamination might spread using computational fluid dynamics. We can rehearse emergency procedures repeatedly with no real-world risk. And compliance documentation that can be generated automatically, consistently, and audit-ready. So the impact is measurable. A 2024 OECD RNEA study found that virtual testing of emergency procedures can reduce real-world risk by up to 60%. Beyond procedural safety, the digital twin directly protects people as well. So it enables real-time radiation field mapping. It can optimize worker trajectories to minimize cumulative dose, and it can trigger predictive alerts when dose thresholds are approaching. And real-world examples are the Sellafield's dose watch system, which use virtual path planning, reduced average worker radiation dose by 25%, according to the UK NDA's 2023 performance report. And that's not just statistics, that's fewer health risks, fewer work interruptions, and more sustainable operations. So we move on to the third pillar, which is logistics. Decommissioning isn't one task, it's thousands of interdependent activities, multiple contractor teams, specialized equipment, and strict sequencing. So the digital twin acts as a central coordination hub. Think like a schedule integration, Gantt charts synchronized with the full 3D facility model. Managers can see progress in context, not just as bars on a chart, but as physical work happening in virtual space. So resource allocation becomes data-driven. Where do we need crews today? Which equipment is available? Where should waste containers be positioned? So platforms like the UK's decom tools deployed at Dunry have demonstrated 15 to 20% improvement in schedule adherence. That's the value of having a single live source of truth. So next up, we will look at a critical subtask within logistics, which is waste management. The challenge: maintain an unbroken chain of custody for radioactive material, from the moment it's cut through packaging, transport, and final storage. So the digital twin solution is a secure digital passport for each waste package. Linked to the virtual model, it carries real-time data on location, radiation levels, and material composition. What about compliance docs? As we said before, auto-generated. The benefits here are full transparency, simplified audits, and smarter use of limited storage capacity. And as the IAEA put it in 2024, digital twins provide immutable oversight of the entire waste life cycle in an industry where traceability isn't optional. That's very powerful. So we move on to look at our case study. So let's ground this in reality. We'll look at the EU's journey from Pleiades to Dorado. So Pleiades built the first BIM-based digital twin platform specifically for nuclear decommissioning. It was successfully demonstrated on 3 real sites in Spain, Norway, and France. Then Dorado takes the foundation and expands it, integrating 8 advanced capabilities, which are point cloud fusion, 3D change detection, an AI dose estimation module called RadTwin, robot mission optimization, and even voice-assisted controls for hands-free operations. So key achievements, well, a common data ontology, a robust server architecture, and seamless integration with international formats like IFC and E57. And most importantly, these tools have been validated in actual high radiation environments. They're not theoretical, they work under real constraints, and they're directly informing new guidelines from both the IAA and the European Commission. So we will look at where everything is heading now. In the near term, we are seeing AI and machine learning integrated for predictive maintenance and adaptive twins that learn from operational data. So AR, VR interfaces like HoloLens are bringing the digital model directly into the operator's field of view on site. On the standard side, blockchain is being explored for immutable regulatory records. The IAA is developing formal digital twin guidelines expected around this year. And initiatives like the Nuclear Harmonization and Standardization Initiative are working to align practices globally. The industry forecast is bold. The World Nuclear Association predicts digital twins will become mandatory for new decommissioning projects by 2030. So to end, let me leave you with 4 quick takeaways. Predictive management, digital twins shift decommissioning from reactive problem solving to proactive data-driven planning. Synergy, robotics, safety modeling, and logistics coordination aren't isolated tools. They're stronger when integrated through a shared digital foundation. Proven value. So recent implementations show cost savings of 15 to 30%, better schedule adherence, and strong safety records. And lastly, global momentum. This isn't a niche experiment. The IAA, the EU, and national agencies are all moving in this direction. So my call to action is simple. If you're considering this for your organization, start small, pilot a digital twin on one subsystem or process, learn demonstration value, then scale. You don't have to boil the ocean on day one. So thank you very much for your time and attention. I'm happy to take any questions you might have.
Thank you so much, Basil. This really puts things into perspective. It's interesting how you told us how digital twins are not just about efficiency, but it's also about responsibility, managing them, complexity, safety, and of course, the long-term responsibility. So if you have any questions for Basil, guys, don't hesitate to drop them up in the chat box. We will answer them at the end of the webinar. So now we are going to move into our third and last speaker, Warda. Warda will connect us with everything back to the core about the topic that everyone is talking about, AI and simulation codes, and how we model atomic behavior itself to design safer systems. So Warda, please go ahead. The floor is yours.
Hello everyone, my name is Varda Tariq and I'm a PhD student in Artificial Intelligence at Higher School of Economics. And today I will present a topic called AI-enhanced nuclear simulation codes. In simple words, this presentation is about how AI can help us better model what happened inside nuclear system so that the reactor design not just safer, smarter, and more efficient reactor design. So let's start. First, I will give an overview of nuclear simulation code and explain why they are important in nuclear engineering. Second, I will discuss the limitation of traditional methods. Traditional simulation methods are not just powerful, they often take a lot of time and computing resources. Third, I will explain how AI can integrate into simple simulation code. Fourth, I will discuss how AI support reactor safety and optimization. And final, in the end, the future trends and opportunity in combining AI with nuclear system. So let's begin. This section introduced nuclear simulation code. Before we talk about AI, we first need to understand that simulation codes are not just the way they matter, so they also show the nuclear field. If we talk about in nuclear engineering, it's not always possible just to go for a safe or affordable to test everything directly in a real reactor. So instead, this engineers build computer-based model that simply simulate the system. These models help predict how the reactor will behave under the different condition at different pressure. So let's talk about nuclear simulation code. Uh, Computer programs are used to react the model's behavior before real reactor is built, modified, and operated. Their main purpose is to help engineers understand what happened inside the reactor under different situations. For example, they simulate how neutrons move through the reactor core and how heat is produced and how that heat is transferred through material and cooling system. The important part is not just because the reactor system must be designed very carefully. If you just see, the one big challenge is not just the nuclear simulation, is that the reactor involves many different physical processes at the same time. This is called multi physical modeling. For example, neutron physics tell us how fusion reacts happen and how neutrons behave inside the core. Thermal systems tell us how heat is generated and moved through the material science and help us understand how reactors material behave under the radiation pressure. Not just this, I will tell you about multi-physical modeling in the depth. This process is not just separated, they influence each other continuously. For example, if temperature change, they can affect materials properties, and material changes can affect neutrons behavior also. Because everything is interconnected, the model must be act very accurate. Even a small error can affect the whole simulation results. That is why nuclear simulation is not just simple. It is present the real reactor conditions as closely as possible. This is also one of the reasons why traditional methods become more computationally and complex and heavy to understand. Now let's talk about the limitation of traditional methods. Traditional simulation methods are scientifically strong and widely used. However, they also have several particular problems, and these problems are one reason why researchers are now interested in adding AI into this process. So the first major limitation is called computational cost. The traditional nuclear simulation requires solving very large mathematical problems because the models are detailed under the reactor system is complex and the computation becomes very expensive. This means we often need powerful hardware such as high performance computing system or a large server to run the simulation properly. Also, many nuclear simulations are large scale. They may include many reactor components, many physical variables, also many steps. All these are increase the processing load. As a result, simulation can become slow. Sometimes it can also take hours, days, or even longer to get results, depend on the complexity. So let's talk about the time, complexity, and limitation. This is also the traditional method rely on advanced mathematical equation and numerical solvers, and this is very useful because it is very difficult to step up this part because of just the time consuming. The more realistic the model become, the more complex the mathematics become. So this makes it harder to perform simulation quickly. Another issue is that traditional method often do not support real lifetime capabilities in order to work. They are excellent for detailed study, but not always suitable when we need a very quick answer during operating, monitoring, or rapid design updates. So after seeing the limitation of traditional methods, the next question is how we improve the situation. One promising answer is artificial intelligence, as AI can learn from existing simulation data and help us to make it faster predictions. It does not replace physics complexity completely, but it can support and accurate many parts of simulation process. Let's talk about first role of AI in simulation. AI can play several important roles in nuclear simulation. First, AI learns patterns from data. This means it studies previous simulation results or sometimes behavior and find relationships between input and output. Second, AI can accelerate prediction. Once trained, an AI model can often produce an answer much faster that runs a full traditional simulation from the beginning. Third, AI can reduce computational load. This is very important because it can lower the need for extremely expensive computing resources in one task. Fourth, AI support decision making. Engineers and operators can use AI-based tools to understand system behavior more quickly and make it better for the decisions. So let's talk about AI-based segregate model. One of the most important AI application in this area is use of segregate model. This model simplified AI model that learns to imitate the behavior of a slower, more detailed numerical situations and simulations instead of just following all the equations every single time. The segregate model gives a fast approximation of the answers. This is helpful because traditional simulation can be very slow. If we already have a good training data, the AI model can learn from it and predict similar outputs from much more faster. So the graph on this side shows the comparison between the prediction and actual values. The idea is that the prediction stays closer to the real value and the AI model is useful. The biggest the advantage, the speed is, the segregate model can make real-time analysis possible. And this is especially where the value is monitoring, optimization, or repeated the designing testing. So now let's talk about AI for reactor safety and optimization. Now let's move on to one of the most important part. In nuclear engineering, safety is always the highest priority, and at the same time, engineers are also wanted to make the system more efficient, and AI can help us with both goals. Let's talk safety enhancement. AI can contribute to reactor safety in several ways. The first is earlier anomaly detection. As AI model can monitor system behavior and identify unusual patterns before it becomes more problematic. For example, if temperature, vibration, pressure, or another variable start behaving abnormally, AI can detect this earlier than the standard rule-based system in some cases. So the second is risk prediction. So AI can not just analyze the part patterns, and it can also do the current data to estimate the risky event, what is going to happen. The third is continuous monitoring. Instead of checking the system only occasionally, AI can help observe it continuously and automatically. Finally, all of these supports of safer reactor design. We engineers know that risk to accept and what warning sign to watch for. You may say that if they create the better safety mechanism, it's helpful for everyone. So let's talk about design optimization. AI can help this with the optimization, which means improving the reactor design and operation. First, it enables faster design iteration. Second, it's also helped to parameter tunings, and third, it can lead to improved performance, better tuning, the faster testing, and it can improve the efficiency, reliability, and system behavior. First, AI can helps to reduce uncertainties. Traditional systems, if you see, the traditional system often contains unknown or approximations, but AI can help us to narrow these, may learn from the data which they already trained. Next, we talk about future direction in AI with the nuclear system. So after discussing the current application, we can now look at the future. This is the combination of AI and nuclear system that it is still growing together. In the upcoming year, we are likely to see the smarter connector and the more automatic nuclear technology. First, you will see in the photo is digital twins. As you know, the digital twins is a virtual copy of a physical system. In nuclear engineering, this means we can create a digital version of reactors and monitor the test in the real time. Second is smart monitoring system. This system combines sensor, data analysis, and AI to continuously observe, perform, and detect issue faster. Third is Trends is a small modular reactor, which is also called SMR. These are smaller and more flexible reactors that AI helps optimize not just to design, control, and also the safety system. The first is advanced automation. In this, you will see that the human workload and not just the human workload, also the monitoring and the analysis part. Overall, the future direction is clear. Nuclear system and moving towards being is not just smarter, safer, and it shows that it is going to be more efficient also. So let's talk about the opportunities. We have the interdisciplinary research, plus we have the career opportunities. If you see in the future, there will be increasing demands for the people who understand both, not just the engineering system, plus the AI also. Also, they will contribute in the global innovation. So countries around the world who are looking for a cleaner, safer, and more advanced energy solution. And final, it supports the sustainable energy future. Nuclear energy, when we manage safety, it can literally provide the stable, low carbon power, and AI can improve its safety and efficiency. So as I already explained, I'm a PhD student in AI at Higher School of Economics. If anyone who would like to discuss this topic or further questions, we are open to answer any questions. Thank you so much for everyone for listening. And these are the QR codes for our social media links. Also, it makes it easier to connect together from different platforms.
Thank you so much, Warda. That was a really interesting presentation. It is fascinating how AI is basically helping us move from slow, heavy simulations to something much more dynamic and responsive. So now this is my favorite part. We have seen the three different perspectives: AI, digital twins, real world nuclear applications. So let's connect them together and go through questions and answers. I would like to start by asking Ali a question, maybe two. First, question is, what type of materials are typically used in building robots that operate in nuclear environments? The second is, how do you control a robot if there is a communication delay or signal interruption?
Thank you, Sohaila, for this question. So the materials that we use three types of materials. First, it's lead. It works as a shield against radiation. Second one, it's electronics that can work with radiation, special parts that don't break easily. Third thing, it's a cheap and replaceable materials, so if the robot breaks, we can replace it without high cost. So it's the answer for the first question. The second question, so we build smart and safety features into the robot. So if the signal is lost or delayed, the robot is programmed to stop and wait until it hears from the operator again. So it will not move or do anything dangerous on its own. Like for some tasks, we also let the robot handle simple, decisions by itself, but it's not working good. We are trying to solve this problem. Thank you for your questions.
Thank you, Ali, for answering the questions. Before we continue with questions, I would like to remind you that if you're watching us on YouTube, you can ask us questions in the comments. We will answer them. One more thing, you can also ask questions not only about the topic. If you have noticed, we have three speakers from three different universities in Russia, so you can ask them any questions related also about their specialization or their university. They can help you, as we are Russian nuclear education ambassadors. So now I will move with some questions to Basil, our speaker from Bauman University. We would love to hear your perspective on this. In such long and complex decommissioning projects, what do you think is the biggest challenge? Is it technical, logistical, or regulatory? And also, how do digital twins actually help decision makers reduce uncertainty in real-time operations?
And thank you very much. Those are both great questions. So regarding your first question, I honestly think it's not one, but it's not one in isolation. All three are deeply interconnected. But if I had to pick the biggest challenge, I'd say it's regulatory complexity because it amplifies the other two. So every technical decision, which robots to deploy or how to segment concrete, and every logistical move like waste routing, crew scheduling, must be pre-approved, documented, and auditable under strict national and international frameworks. So a small change on the ground can trigger weeks of reapproval. And that's actually why digital twins add so much value. They let us simulate, document, and validate decisions in advance in a format regulators can review. So while the technical and logistical hurdles are significant, the regulatory layer is what makes agility so difficult, and why digital coordination isn't just helpful, it's essential, really. And regarding your second question, so there are three concrete ways. So first, situational awareness. By fusing live sensor data, radiation levels, robot position, structural readings into the 3D model, decision makers see not just what is happening, but where and in context. So it eliminates the need for guessing from fragmented reports. And second is predictive foresight. So the twin can run rapid what-if simulations. So if we shift this screw, how does dose exposure change? If this valve fails, what's the contamination spread? And that turns reactive decisions into proactive ones. And the third is traceability. So every action, who did what, when, where, and under which parameters is logged automatically into the model. And that reduces ambiguity during handovers, audits, or unexpected events. So in short, the digital twin doesn't eliminate uncertainty, but it gives decision makers a shared dynamic evidence-based picture to act from. And that's how you turn complexity into confidence, pretty much. Great question. Thank you very much.
Thank you so much, Basil, for answering our questions. And now we have a couple of questions to Warda. With AI becoming more integrated into simulation codes, how could we ensure that the results remain reliable and trustworthy? That's the first question. And the second question is, do you think that AI could eventually replace traditional simulation methods, or will they always need to work together?
So for the first question, to just ensure that AI-based simulation results are reliable, we do not rely on AI alone. We validate that AI model using traditional physics-based simulations and the known data. We also test them under different conditions to check their accuracy. So AI is always checked and supported by trusted methods only. And for, the second question, which is that if they replace the traditional simulation, right? I think AI will not completely replace the traditional simulation method. Instead, they will work together. Like traditional simulation methods are based on physics and give very accurate and reliable results, but AI, on the other hand, is fast and efficient. So the best approach is just to combine both, using the traditional method for accuracy and AI just for make the things speed up.
I agree with you totally, as myself an automation control systems engineer. Thank you so much for your explanation and your answers. And now we will take some questions from the chat box. I see people are very excited, our listeners very excited to ask you questions. So we will start with the question to Ali. What are the techniques being used to train the robot? For example, does it use computer vision techniques or reinforcement learning or both?
So thank you for this question. My answer is both of them. Actually, we use reinforcement learning. So the robot learns by trying actions and getting rewards like trial and error. And also use computer vision. The robot uses cameras and sensors to see and understand its environment, like detecting cracks or finding pipes. Sometimes also combine both techniques to make the robot smarter and more independent. Thank you for the question.
Thank you, Ali. Now we will move to a question to Basil. Does the IAEA have plans to implement a uniform standard for training AI models for digital twins, given that not every country has the resources to constantly train models? Is this something that is taken into consideration?
Well, that's a very timely question, and you've touched on a critical issue, which is equity and access to advanced digital tools. So, to be direct, the IAEA does not yet have a uniform standard specifically for training AI models for digital twins, but that is actively evolving. So, what we do is a two-track approach. Firstly, is foundational standards. So, the IAEA is developing broader digital twin guidelines, expected also around this year, focused on data formats, interoperability, and safety validation. So, not the AI training process itself. Projects like Dorado are contributing by establishing common ontologies and open formats like IFC and E57, which lower the barrier for countries to adopt these tools without building everything from scratch. And secondly is capacity building. So the IA has long prioritized technical cooperation programs that help member states access shared knowledge, training modules, and pre-validated models. So the idea isn't that every country trains its own foundation models, but rather they can adapt and fine-tune shared peer-reviewed models to their specific facility context. So while a uniform AI training standard is not on the table yet, the direction is clear. So open architectures, shared validation, frameworks, and cooperative capacity building. And that way, advanced digital tools support global safety without widening the resource gap. And I'm also happy to point out that the IA's technical meetings on digitalization, if you'd like to follow the developments more closely.
Thank you so much, Basil. That was a very detailed answer, and thank you for your information about the meetings and informing our listeners about it. Now there is a question to Warda. How do engineers handle hallucinations in complex physical-based AI models?
So I think like the engineers reduce his hallucination by making AI follow real physics rule using which the method is called physics-informed neural networks. They also check AI result with simulation and real data to make sure that they are correct. And if AI is unsure or give unsafe result, in simple way it is rejected. In any ways, in the most important, the last step is always the human who will review the final and the last output.
Thank you so much, Warda, for your answer. And we have one last question about digital twins. Thank you, Johnson, for listening. Can you give us an example of how digital twins have successfully predicted unexpected events in real nuclear systems?
So
It's from
I can answer this question. Or
You can
to,
both.
to
First, Ali
whom?
can start, then our other speakers can also contribute. Please go ahead,
So
Ali.
thank you, Johnson, for this question. Like how I said already, the digital twin has predicted, like let's say, like digital twin predicted that cooling pipe would fail in 6 months based on stress and other things. So engineers sent the robot to inspect the pipe. The robot found that the pipe was actually fine. There is no any problem there. So the digital twin was wrong. So it's learned from the real data and corrected its model. Um, this is still a success because the digital twin was updated and became more like intelligent for the future predictions. So it saved the plant from unnecessary shutdown. That's the example I can give you.
Thank you, Ali. Any other speakers would like to contribute? Warda, did you want to say something? To add something? Would you like to?
Yeah, I think like digital twins create a live virtual copy of a reactor, not just to miniature, but it's also behaviors. And they can detect unexpected issues like he said, like water level instability or system of function earlier. But this helps engineers to take actions before problems become serious. So they improve safety by predicting events that are harder to easily see.
I see. Thank you so much, Warda, for your added contribution. And if our speakers don't have any other things that would like to share with our audience, I would like to highlight something before we end our webinar, that today we didn't just talk about nuclear energy. We talked about how we understand the invisible, predict the uncertain, and operate in the impossible. And that's exactly what happens when students come together and we share knowledge and build something bigger than ourselves to help us understand more the field that we are going to work on and with in the future after we graduate. So, because at the end of the day, we are students for students, connected by atoms, driven by youth. Huge thanks for our speakers, Ali, Basil, Warda, for joining us in today's webinar. This webinar was really engaging and insightful. And as we see, it was interesting for our listeners. And thank you all, our listeners, for being here, for listening to us, for joining us. We would like to see you in our next webinars. Please follow us on our social media to stay updated about our upcoming webinars. You can ask us questions in the YouTube or in comments on our socials. So see you again in our RNEA next webinar, or maybe in person. Who knows? Bye.